Okay.
Piyush, can you make the slides a little bigger?
Yeah, I'll make it. Just a minute. The slides are visible, right?
Yeah, they are visible.
Yeah. Okay. I'll go to full screen, so then we will. Zoom always gives me problem with.
Is it RC Linux or something?
Now visible, right?
Yeah, yeah.
Let's start. Okay. Okay. So, firstly, thanks for inviting me for this ISLA meeting. So, I just want to know, maybe in the chat you can mention how many of you have kind of used a proof assistant. If there, I mean, since we are, if there is someone, how many of you have used to prove some small theorems once in a while or something? In the chat, if you have not used, you can say no, so that I can know. Okay, so yeah, so I think we have interesting case here. So, what I'm going to talk about is a deep connection between programming and proving, and which has been kind of known for quite some time. And there are many systems built out of this connection. And recently, it has become practical also to prove large code bases. So I think the time for starting to use proof assistance have really. Okay, so I'll be talking about this proof assistant called COF. So it is it's a proof assistant based on this type theory called calculus of inductive construction. Well, we don't really need to know what the details of that type theory is. So this set of lectures, my plan is to introduce you to the world of proof assistance through this proof assistant COF. And what I want to say is that I mean, it makes sense to, I mean, proving things formally requires interaction, and interacting with the proof system is very much required to work with a proof system. Otherwise, it's just impossible to write forward. So, if you want to get your hands dirty, then I suggest you start installing COF and trying it out. At least for small theorems, you can try it. Okay, so let's start. A proof assistant is the following. It's a kind of software which will take some proof that you have written and kind of check whether the proof is correct. Okay, so it is not going to prove it for you. It's just going to check whether the proof that you have written is correct or not. Okay, so one can think of building a proof assistant just like that. I mean, you know that there are the rules of logic, and you can write a kind of program to actually check proofs. But it turns out that it is better to do it in a slightly different way. Okay, so in the world of programming languages, you have programming programs, and they often have some notion of types like natural numbers, strings, those things, and you have what is known as a type checker, which when you give an expression of some type, purportedly of some type, it checks and sees everything is correct. For example, it checks whether, I mean, if you're trying to add a number to a string, for example, it will tell you that there is an error. You can't do this. You can only add integers. You cannot add a string to a string to a number. Okay, so this is kind of a well-known thing in programming language. I mean, if you have used any kind of programming language, you know this. So the point here is that there is a connection between these two worlds. It's often called the proposition as types principle. What it says is that if you look at proof checking, where you are given a mathematical statement, I hope my mouse is visible.
Yeah, visible? It is visible. Yeah, it is visible.
Yeah. So on one side, you have the world of mathematics, where you have statements about some stuff, and on the programming side, you have types. which are the corresponding objects to mathematical statements. Okay. And you want to check you want to kind of formalize the proof of a mathematical statement, let's say A. You can see this as building a value PF of the type A. Okay. So A, remember, is a type which corresponds to mathematical statements under this correspondence, and giving a proof of A is essentially building a value of type A. Okay, and the main idea is that if you have a programming language with a sufficiently advanced type system, we will see what kind of advanced type system we need. It can also work as a proof assistant, where the proof assistant being just checking whether a given expression is well typed or not. Okay, so I would like to kind of look at it from the perspective of programming here. Although you could kind of formalize most of mathematics this way, but for software development, a particularly interesting consequence of this thing is you can do what is known as certified programming. Okay, so what is certified programming? We want programs with formal proofs of correctness. We want to prove the correctness of the program. And when I say formal, I mean machine checked. So the proofs are actually machine checked. Why do we want it? Of course, bugs are annoying, and if our programs are supposed to do some really critical things, it can be quite dangerous if there is bugs in it. Okay, and if you have a proof assistant of this kind, where it is based on this theoretic type checking word, the proof proposition as types kind of idea, then what you can do is you can write a well-typed program in Coq, and the type, if it's if Coq agrees that your program is well-typed, that is like the type actually captures the proof of correctness. And so you have a program which is now written in Coq, it's a language, and a programming language in that sense, and also the proof. Okay, I mean, the correctness proof is also written in the same language. And what you can do is you can take this code and extract some OCaml or Haskell code out of it, which can then be executed, and thus you have a program which is kind of checked for correctness. So this is why, as a process for if you want highly reliable software, you probably need to do something like it. I mean, you can try to use some proof system. So just to kind of give you an kind of workflow of how you would go about it, you start by writing the program, and Coq will type check it. If it fails, you go back, edit your program, and keep doing this till it succeeds, and then you can do this thing called extraction. So maybe you can extract it to OCaml, and then use OCaml compiler to get an executor, which is what you will deploy. Okay, so what I will do is I will in this 2-hour talk, what I'm going to do is I'm going to kind of quickly introduce you to some concepts in Coq, and then we will do a live session. So that is what I plan to do. So the first thing is I'm going to introduce to you functional programming in Coq. Okay, because remember, ultimately Coq is a programming language. Okay, so let's start. So I mean, if you want to kind of use Coq in some serious way, you should probably install Coq. You should install Emacs with a mode called Proof General. So Proof General is a Emacs mode to work with Coq and other proof assistants. And optionally, you can install what is known as a company Coq extensions. This will give you some extra bells and whistles on top of Proof General, like some pretty notations and things like that. Okay, so this is optional. You probably don't need. Even Proof General you can avoid. There is a Coq IDE that you can use. But if you want to write and maintain even a slightly big kind of project, you probably need to use this proof generator. But once in a while, if you just want to kind of play around with it, you can use a Coq ID that comes with Coq. I mean, most of the Linux distributions have it, so you can just install it. Okay, so let's get into the kind of basic syntax of Galena. Galena. So Coq consists of 3 languages. Galena, which is the functional programming language underneath Coq. Then there is something called vernacular, which is kind of these are kind of commands that you give to the Coq interpreter. Okay? And then there is LTAC, which is a tactic language. We will look at this in detail when we do the interaction. Okay, but so mostly I will be bothered about only Galena as of now. Okay. So yeah, you have values like 42, and they come with a type like NAT. Something like true, for example, is of type Boolean. You can form Cartesian product of 42 and true, and they will be of type NAT star bool. This is the type of Cartesian. This is a type of pairs of natural numbers and bools. And the syntax for a function is somewhat like this: fun x of type NAT, and this equal to arrow. This is like, you should read it as a double arrow. So you should read this as x is mapped to x plus 1. Okay. And this has type NAT arrow NAT. So the arrow, just like in mathematics, denotes functions from natural numbers to natural numbers in this case. And yeah, so in when you are working with Coq, you can try to check those expressions. So you can write check and give a number and give a dot. And all commands end with a dot. So the check is what I called a vernacular command. So check of 42 will ask Coq to check the type of 42, and if it is successful, it will kind of print the type. You can type check true, it will say it is Boolean. You can check 42 plus 2, it will say NAT. And if you say check 42 true, then it will say NAT star bool. And if you do something like fun x in NAT x plus 1, it will say it is of type NAT to NAT. And if you write the constant function true, fun x in NAT to true, then it will say it's a function from NAT to. Okay, this is kind of straight. At any point of time, please feel free to interrupt.
Piyush, I had a question.
Yeah, sure.
2 slides. Could you go 2 slides back where you were explaining what the process would be for type check for this one? Yeah,
This one?
just after
Yeah.
that. Yeah, over here. Certified program. So you said that if we have a program, we have, like, suppose the program is written in Java, and then someone would write a proof.
No, that is not possible. You should write the code in Galena. So the Coq system consists of three parts. One is the functional programming language. It's called Galena. Okay.
Right.
And then vernacular, which is just like I showed you the command check. That's a vernacular. There are other vernacular commands also. Okay. So new types and making new definitions and things like that. And so you essentially program in Galena. So Coq is also your programming language.
Right, and the proof will also be written in Coq, and then
yeah, and Coq type checker will check it. If it fails, you keep on editing it till you get it passed through the Coq type checker. And once the Coq type checker is I mean, when it is kind of when that happens, you are happy. What you have is now a program written in COP, which you know is correct. Of course, this you cannot execute. Okay, so what you are going to do is
Correct.
you are going to then extract into some language like OCaml or Haskell, or I think they also have Scheme backend. So you can extract OCaml, and this is the thing that you compile through the OCaml compiler and run. So this is how you get a
I see.
executable which corresponds to this program. So that is the workflow that you have.
And
You cannot
I know it might be early to ask, but how does a proof of a program look like? Like a proof of a program is also going to be a program, but what would it look like?
So what happens in this context? We'll come to the details when we actually try our hands on. I'll have a live session coding. We'll see that. But essentially, the point is that there is no such thing as programming and proofs. You just write a program, okay, which is well typed. The well typedness of the program captures its correctness. Okay.
I see.
See, so let me give you an example. Suppose I write a Java program and run it through the Java compiler, and I don't get any error. Okay. What can I say about the correctness of the code? I can say one thing for sure. For example, I would not have added an integer to a string. I could have said that. Okay. Right. Why? Because the compiler will catch such a thing. Right? If you try to add a string to a integer, it will say, okay, these are not compatible objects. You cannot just add whatever you want to strings. So it will give an error. So in some sense, you can think of it like a proof check. I mean, kind of proof checker, where all it checks is that you don't make any error of the kind adding integers to kind of strings. So suppose your only specification that you want to say about the program is that it will never add an integer to string. Okay, if that is the theorem that you want to prove about your program, not anything interesting like it will sort or any such thing, then this is a good enough proof assistant in that sense. Does that make sense? Okay. So here what will happen is that
if I have a
so here what happens is that
I have a slide. Yeah, go ahead.
So if so if in this context, what happens is that your type system is very powerful. So you can express much more than just saying that you are not adding integers to it. You can say more powerful. So that is how the correctness is done. Okay. So this has particular consequences. We will see how that is. Okay. Most likely, I'll try to do in the next lecture a complete kind of example of a toy compiler. Okay, so we can have a look at it.
Thanks.
Okay, so let's move on. Okay, so that's good. Please keep asking, because I think not many people are familiar with these topics, so it is good to always ask. Okay.
So I have a question.
Yeah, sure.
So you said ki like, sorry. So you said ki like it can do the type checking, but like whether the program can do sorting or not. So my question is whether COC or any of these systems can also check whether the requirements of the user and all there.
Yeah. So the point is that things like whether this program sorts or not, this you can express as a type. Okay. So when you write, so you can write something of this kind, that sort is a function which takes a list and produces a list, but with a guarantee that the output list is sorted. Something like that you can get that. Okay. So we'll see this. We'll see slowly how this is. Okay. Okay. So in principle, you can prove anything you can think of. Wherever, I mean, anything that you can kind of hopefully, I mean, not anything you can think of, but any correct statement, you can mathematically correct statement, you can probably hopefully prove it. Okay. But we'll see that.
Okay, just so we can also prove its correctness, like
correctness of what?
COC as it's working.
No, that you cannot do. You cannot prove the correctness of COC with COC, because that again has been coded. So what you need is, you always need a kind of trusted kernel, the part which you trust, and everything else depends on that correctness of it. Of course you cannot. That's always you cannot go avoid that. Okay. Okay, so the main idea here, as I was trying to say, is that mathematical statements can be captured as types in your language. Okay, and producing a proof of that mathematical statement is equivalent to producing a object of that given type. Okay, so if A is a mathematical statement, we'll look at specific examples when we come to that. Okay, so yeah, so we were here. So 42 is a Galena expression, and check of 42 asks the COP system to check the type of this expression, and if it is successful, then it will print the type. So let me just maybe I think it's a good time to just switch this and go to the interactive mode. Let me just give you an idea of how it looks like. So for example, this 42 expression is here, and I'm asking it to check it. So let's actually run through this. Can you see that on the bottommost screen, you can see 42 written, and you can see colon nat. Okay, so I'll just switch off the company prompt. That you can. So I asked it to check 42. So it tells me in the bottom screen, you can see that it says 42 is of type nat. Okay. Similarly, if I ask it to check true, it will say true is of type 42. True is of type bool, and 42 plus 2 is of type nat. Say if I try to do this, something like some silly thing like this, then it will say that true has type bool while it is expected to have type nat, which is like the classical type kind of error that compilers typically issue. Yeah, so we see that we have tuples. This is a function of type nat to nat. You can see that fx to x plus 1 is a function from nat to nat. I can try to execute that. It will give me the execution of this. So I applied this function on 41. It takes 41 as arguments, increments, and gives backwards. Okay. So this is plain simple program. So we will look at more live sessions later. So let's come back to the other screen. Okay. It's visible, right?
Yeah.
Yeah. Okay. So the point here is that what you have is what looks like a programming language. There is values or expressions, and you can associate it with types. And all that the COP system checks is whether the thing that you give is a well-typed object or not. That's all it takes. Okay, so that is the simplicity of the thing. Okay? It's a very simple language. It's a very simple language. It's a few constructs, very few constructs, and all it does is check the type of a given exception.
There are also lists.
Yeah, all those things are there, and you can build your own type. Okay. So, for example, let's build our own Boolean. So the standard Boolean values, Boolean type is called bool. So you can define a new type called Boolean as follows. Okay, you can say, you can use the keyword inductive Boolean equal to either it is true or it is b false. Okay, we have created a type now which has two constants. One is b true and one is b false. So you can check this and figure this. We will do that in an interactive session. So what this gives you is a new type Boolean and two constants, b true and b false, and no other Boolean values. This is what it gives you. After you type, so the command here, the inductive command is a vernacular, so to say. Okay, and this vernacular, what it does is it kind of leads to the construction of a new type called Boolean, which has two constructors, b true and b false. And there are no other Boolean values. So, and you can do you can write functions by case analysis. For example, you can have a not of this Boolean as follows: b not of, so definition b not is the name of the function. It takes one argument b of type Boolean and gives out a Boolean, and is defined as to match b. Okay, so you are doing a pattern matching or case by case analysis on b, and if it happens to be b true, your value of the function is b false, and if it happens to be b false, your value is b true. It's a simple pattern matching. Similarly, for example, you can define and as follows: if you try to match a with true, if it is true, then its value is essentially what you have b. If a is not true, or if this pattern is not matched, so the underscore means you match whatever. Okay. So the way you read this match statement is you try to match this value with the first one. If it succeeds, then the result is the thing after this arrow. Okay. And if this doesn't succeed, you go to the next pattern. Okay. In this case, it is underscore, so it will match anything. Okay. And if a fails to match b true, then it will always return b false. So this is how we define. Okay, so now let's look at something like natural numbers. Okay, I mean, if you want to do any kind of proving, you need natural numbers. Right? So so how does one define mathematically what natural numbers are? You can start by saying that, okay, natural numbers consist of a few rules, right? So a few inductive rules. What is the two? In fact, two inductive rules. Okay. What are they? 0 is a natural number. That's the first rule. The second rule is if a is a natural number, then so is successor of it. Okay. So the smallest such set is called the natural number. So you can say that 0, successor of 0, successor of 0, etc. are the only natural numbers. This is how you would have kind of seen this in let's say a course on set theory, basic set theory. Yeah, so the keyword inductive can be used to build natural numbers as well. So naturally, you can kind of capture it through what is known as constructors of the type. So here you are saying that nat is defined inductively as follows. There are two rules. The first rule says 0 is a natural number. Okay. The second rule says is successor is a function from naturals to naturals. So in the sense that this says that if n is a natural number, then successor of n is a natural number. Okay. And the smallest set is captured by the word inductive. Okay. So once you define this, you have now produced a data type which corresponds to natural numbers. Okay. The standard library natural numbers also look like this. Okay. The constructor name might be different, but that's it. So this is the natural numbers are not inherently there in Coq. It's part of the library.
I just have a small doubt. So you don't care about this first letter thing? I mean, type constructor can be like
Yeah, yeah. Some languages like Haskell and even OCaml have this restriction that you cannot use. For example, Haskell type values have to start with capital letters. You can't have small letters, and constructors have to be capital letters, but variables have to be small letters. There is no such restriction in Coq. The reason is that in something like Galena, the distinction between values and types slowly erases out. Okay? So that is the reason we don't want to kind of do such a restriction. That it will be a painful affair. So we'll see that there is a reason for not having. For example, you can have functions which take, say, a natural number and produce a type. This is possible, right? So you don't want to really distinguish between values and types in that sense. Does that make sense?
Yeah. Okay.
Okay, so shall we move on?
Yeah.
Okay, so now let's look at something like addition, okay, of natural numbers. So addition, again, you kind of recursively define it as follows. You say that, okay, let's talk about adding 0 to some natural number x. So 0 plus x is x. You do that. Okay, if you want to add successor of x with y, then what you do is you add x to y and then take its successor. Okay, and by doing this, you have kind of completely specified what the plus function is, because now you know how to kind of compute the sum of two natural numbers. Yeah, so the corresponding thing in Coq is defined again through pattern matching, but this time what we cannot use the word definition. We have to use what is known as a fixed point. Okay, the reason is that plus is recursive in itself, so it cannot be a mere definition. It has to be a fixed point. Okay, so again, it takes two arguments, a, b of type nat, and produces nat. And the way you do it is you match a with 0. If a is 0, then plus ab is b. If a is successor of ap, then plus of ab is successor of plus of apb. Okay. So for example, you can do define 2 as successor of 0, and then you can compute 2 plus 2. Okay, so we will see all this in an interactive setup soon, but yeah, so this is essentially the way.
But it should be possible to give a definition of plus using definition only, no? Like you use in Haskell also, you can write the same thing, but you don't have the fixed point.
Yeah, so in Coq, you have to be careful about recursion. Coq does not allow you to do arbitrary recursion, okay, unlike Haskell. All programs that you write in Coq have to be terminating. This is a requirement, because if you don't have that, then the type system of Coq will fail. So fail in the sense that you might accept proofs which are not correct. So you need that kind of a restriction. So you kind of have to be careful about recursion. So so you have a different word for defining recursive objects. Okay, so that's fixed point. Yeah, we will look at. Yeah.
Is there a reason for using the name fixed point?
Okay, so there's a reason for this. You might have you done a course on lambda calculus?
Yes.
So you might have done this fixed point theorem in lambda calculus, right? That every function has a fixed point.
Yeah,
that's a proof.
right.
Yeah. So actually, fixed point and recursion is actually computing the fixed point. That's the reason. Okay, it's a computing a fixed point of a given function. Okay, so that is the reason why this is called fixed point. So you can write plus, you can write it definitionally also. You can, strictly speaking, you can write definition plus equal to, and then you can write a fix of some function you can write. Okay, but I've just been slightly loose here. Strictly speaking, you can use definition, but it's just inconvenient. It is easier to think in terms of recursion. But yeah, that's the thing. So fixed points and recursion are essentially the same things. That is the reason why you have this word fixed point. We will also see this. Okay, just remind me during that interactive session. You can also write theorems. For example, you can write something like this: the left identity for all n in NAT plus of 0n is n, and you can prove it, and the proof is rather trivial. You can also prove the right identity theorem, which is for all n in NAT plus of n 0 is n. Unlike the previous case, it's not theorem. You have to use induction to prove it, and yeah, you can see that in COP also there is some steps involved in proving this right identity. Okay, so that's we'll see this again in interactive mode in detail. Okay, so this is how you can do things. Okay, now let's come back to the point. So for time being, ignore the fact that there are some new things here, but let's go back to our certified programming kind of setting. So you can think of, let's say, suppose your task was to write the plus function for natural numbers. Okay, and you wanted to you have written some function here. Yeah, so this is your program that you have written, and in some sense you have written the some theorems about plus. Okay, in a software development world, typically how it goes is you write functions and work programs, and you write test cases, for example. Okay, so you can think of this like a test case. You have not completely proved that plus is actually the addition, but what you have shown is that under plus 0 is a identity, which kind of gives you confidence that plus is probably the right thing. Okay, and here instead of writing it as a test case, you can actually go ahead and prove it, and you know that it's correct for all things. Okay, similarly, you can also show that 0 is the right identity, and here also you can give a proof for it. Oops, something went wrong. I move the mouse, something happens. Okay. Yeah. So does this make sense? So imagine that you were tasked, a company kind of gave you $1 million to write a formally certified plus program, and you have written it, and that the company, since is giving $1 million, it wants good assurance that your plus is really plus, and so you gave the certificate that, well, it is difficult to say what it means to say plus. I mean, plus in some sense, the plus here is more or less the specification of the addition, but at least you can prove claims like this. You can prove these theorems and convince the company that their dollar was well spent on writing a certified plus.
Piyush, I did not understand this part. These are essentially analogous to test cases.
These are analogous to test cases, but the difference is that here it's once you finish the QED part of it, you have done the proving, which means that you don't write. It is not like you run it on some cases and check. What you're doing here is that you're actually proving that this plus is always going to be correct.
Yeah. So I'm thinking like for statements that involve for all n, like how would someone computation, like how would a computer even prove this? Like,
yeah. So it is not going to go over all natural numbers. What it is going to do is that is the climax of this part. Is for all n in NAT plus 0 n equal to n, the thing that you see after this colon, right? Left identity colon something, right?
Right.
This object for starting from this for all to this full stop is actually a type. It doesn't look anything like natural numbers or anything, but it's a type. Okay. And what it is, when I write the statement theorem left identity colon type, I am essentially saying to the COP world that, look, now I'm going to give you an element called left identity, and it is going to have this as a type. And in this proof to QED part, I am actually constructing such an object. Okay, we'll have a look at it. Okay. So what is happening here is not that it is going to run over all NATs and check. What is happening here? It is just doing a type checking.
I see.
Okay. So, and the type checking here is, decidable. So it can kind of conclude whether the proof is correct or not. So that is the difference. Okay. So an equivalent thing, if you look at the software development world, you might have seen some these quick check kind of tests where you give a condition like this, plus of 0 n equal to n, and it will try out for random test cases. Or you have something like a exhaustive testing case where in a range it will exhaustively test. Here, nothing like this is happening. It is actually checking for types. Just like it checks when you do n plus some hello string, it figures out that there is a problem in types. Similarly, it will figure out if you have given a wrong proof here. That's what is going to happen. Okay. Okay. So I also want to spend some more time on this slide, although you might not have got exactly what these things mean. But here, so again, the statement that I have written, this theorem is a vernacular command. Okay. So by proclaiming this theorem thing, I am saying that, look, I am intending to write I am intending to give you a value left identity whose type is this object for all n at plus 0 n equal to n. And then again, a vernacular command called proof. And in the process, I am using what is known as the tactic language. So I am not writing this thing directly in Galena. I am using a tactic language to write it. And that is the third object in your Coq Trinity. One is Galena, the programming language, the vernacular, which is the management kind of thing, and LTAC, which is a tactical language, which will help you write proofs. Okay, you can think of LTAC as a kind of macro system, which kind of writes the complicated expressions for you. Okay, so strictly speaking, you only need Galena and probably vernacular to build new types and things like that. But LTAC is not necessary, strictly speaking. Okay, you could have written this proof as a definition also. Okay, but LTAC is convenient in many ways, so that is also good to know. Okay. Which also means that you don't have to trust LTAC. You can use a completely arbitrary tactic to try to prove some claim. You can use a completely vague heuristic. Okay, your LTAC might be buggy, but that doesn't break the trust in the system, because anyway LTAC is not trusted. Okay, LTAC will generate an expression which the Galena type system will check. Okay, only when that check has happened will Galena be satisfied with your proof. So LTAC can be completely arbitrary. Okay, LTAC can be as idiotic as just randomly write some code. Okay, I mean, you can write an LTAC script to do that and hope that it will prove the Riemann hypothesis, for example. But the Coq type checker will catch you if you write some silly statement. Okay, so I hope you are getting a feel of this. We'll kind of go in some more detail when we do the interactive session. Okay, so let me summarize the functional programming aspects of Coq. So you can define types using inductive definitions. You can define functions by means of pattern matching, and recursive functions you can define using what is known as fixed points. And finally, you can prove theorems using tactics. Okay. So any questions here? We will now switch back to our interactive session.
Yeah, so in the beginning you said dependent types, but so far we haven't used them. Yeah,
we haven't used that. We will see that.
So right now we are still in only the type system available in, let's say, Haskell and Workamer.
Yeah, only that. Okay. Let me just
when you say a theorem, it can be any first order statement using the functions and Boolean operations available?
More than function first order, because you can also talk about functions.
Yeah, but first order quantifications, functions which you can define and existing, and Boolean operations. Is that it?
Sorry?
Like a theorem statement is first order quantification.
Not just first order. It's a higher order logic, because you can define functions which take functions. So it is higher order in that sense.
But you can't quantify over them, no? Can you?
You can quantify over them as well. You
Okay.
can say things about functions.
Uh-huh.
I mean, you would want to do that, because you would want to say that if would want to say something like, if you give me any function, then I can do that. Those kind of things you might want to do. Higher order functions are there. Just like Haskell has higher order functions.
Yeah.
Where the logic is higher order. Yes.
Yeah, but that I understand. But I was talking about quantification.
Yeah, quantification is a kind of function. It's dependent functions. Okay, so for all quantification can be seen as a dependent function, which we'll see in the next session. Okay, so let's go over it interactively. Any other questions? I am making it full screen, but then when I have made it full screen, I am blind. I cannot see any of you. So you'll have to speak out if you have to. Okay, so yeah, we saw this. We get some things, and here is the definition of Boolean. Okay. After this point, so let me do something like this here. Let B2 here before I define the Boolean. It will say I do not know what B2 is. Yes. But, okay. So after this point, Boolean is defined, and then if I do a check on B2, it will say that B2 is Boolean. I can do B false. That's also Boolean. Okay, so now let me try to give you a lemma which says that the only things that are Boolean is either true or false. Okay. So all bools, this lemma says that lemma and theorem are all the same. Okay. This lemma says for all B, okay, in Boolean, either B is true, or the or is written as slash and slash B equal to false. Okay, so this is what I want. Okay, so now, yeah, so so let's do the proof. So the intros is a tactic. What it does is it kind of assumes the first thing. Okay, so notice that when I did, so just before look into the middle window. You can see the middle window. Yeah. So in the middle window, you see a horizontal line. Okay. So below the horizontal line is the thing that you need to prove. Just a minute. I'll just close the door. Yeah. So okay. So what you see is a horizontal line. Below the horizontal line are things that you need to prove, and above the horizontal line are things that you have with you, which you can use to prove the claim that you have. Okay, that you have to prove. Okay. So when I do an intros, what happens is that this for all B travels from here to here. Okay. So this is the standard mathematical thing. So let's take any arbitrary B. That's this intros does that. Let's take an arbitrary B. Okay. Great. So what I am saying here is, okay, I have an arbitrary B which is of type Boolean. I have to show that B is either B true or it is B false. Okay, and there is this tactic command. So this intros, distract, intuition, all these things are tactics. Okay. Statements. So when I do a distract, what I'm saying is that try the case by case, do a case by case analysis on B. Okay. B is a boolean is given, and the fact that booleans are defined inductively means there are only two possible cases. So let's do the two. Okay, I'll do it in do a distract. So when I do a distract, I will have two goals. Okay, B has gone off, and I have taken the two cases. The first case, I have to prove B true equal to B true or B true equal to B false. Okay. Clearly, I will essentially go ahead and prove B true equal to B true. Okay. And the other goal, I have to show that B false is B true and B false is B false. Or sorry. Okay. So this is what. And the tactic intuition kind of disposes all these things. So I can, there are two cases. So let me do it separately. Intuition and intuition. And then you see no more goals to goals at this point. And then I do a QED and Coq is happy because the proof has been accepted. Okay. Yeah. So at this point, I want to kind of pause a bit and kind of show you the proof term. Okay. Remember that ultimately, whatever you do with tactics is generating a term which has this type. Okay. Ultimately, remember the propositions as proof principle. If I want to make a mathematical statement claim like this, that for all B boolean, B is true or B is false, that's a mathematical statement that corresponds to a type or prop in this case. Okay, it corresponds to a type, and all that is involved in proving it is producing a object called all bools of this type, which Coq's type system can convince. So I can kind of show you what the proof term is, and I'm kind of almost sure that it is not something that you will like to see. So it is this. It's not that bad, but it's not something that you would like to write. Okay. So I mean, we will see even worse examples. So just hold on. So notice that this is the object that we have created. Fun B in bool, match B as B0, return this thing with B true being or intro of equirefill and or intro of equirefill. What these things are, you don't have to bother. Okay. But the point here is that this is the object. This is the proof object which convinces Coq that the statement is true. Okay. I can actually do that. I can just of lemma, I can do a definition. I don't have to use any alt tag. I can just get this expression right away. And that's enough. Okay, I could have done this. Okay, so although the proof world and the expression world looks different, they are actually the same. Okay, so I just kind of gave you an example of how to do it explicitly. Definitely, you wouldn't want to write this by hand. Okay, so let's move on. The boolean not. So I just compute B naught of B true, B naught of B false. I compute B and of B false and B false, B and of B false and B false. Let's prove some interesting lemma here. Not lemma. For all B, what is the not lemma?
Not B equal to B.
B naught
of
B naught of B equal to B. Okay, again we do the favorite step, intros, and essentially destruct. See what happens. You do a simple, and then you can finish the proof this way. Okay, so again, whenever you do this, at least in the beginning, you might want to have a look at the term that you didn't have to write because of tactics. Okay, so again, it is not very complicated, but you definitely don't want to write this. Okay, so now we go to our inductive natural numbers. Define the plus of AB as A 0, then it is B, and if A is a successor of AP, then it is plus of AP, and it's a, I can print, and you can see that is defined like this: plus equal to fix of plus A. It essentially says take the fixed point of the function plus, which takes A and B and gives this object. Okay, we can cover this as follows. Okay. That's the fixed point way of looking at it. Okay. So in principle, you can use a definition here with plus equal to fix plus AB, whatever. You could write this. Okay, but it's much more convenient to write this. Okay, we move on. Any questions so far? Okay, so let's move on if there are no questions. Successor of 0. There are none. Yeah, plus of 2. Yeah, left identity theorem for all n in that plus 0n. Then this again is a trivial proof because this is by definition. Okay, this is true by definition, and that is why this theorem is trivial. Whereas the right entity is not true by definition. You have to do some work for it, and that's the thing. Again, we do an intros. So intros is like, say, let's take an arbitrary n. Let's do induction on n. So induction is kind of more. So you looked at destruct, which is case by case analysis. Induction is usually in the case of natural numbers, it is a Peano's induction step. But you can think of it as a destruct with steroids, right? So you do induction on n. So there are two goals. The first goal says plus of 0 is 0. That is trivial, and that you dispose of. The second claim, let's move on to the second claim. It says I have a natural number n, and I know that by induction I know that plus of n0 is n, and my goal is to prove plus of successor of n0 is successor of n, right? So I just simplify the goals. So when I simplify, I get successor of plus n0 is successor of n. Okay, this is what I have to prove. Okay, but I can use this induction hypothesis. I rewrite it with the induction hypothesis, and when I rewrite, so remember the induction hypothesis is rewrite means replace the LHS of this equation, in this case IHN, with its RHS. So this plus n0 will become n after the rewrite. And since you want to prove successor of n is successor of n, that is trivial, and we have done the proof. Again, for the sake of horror, let's look at it. And this is definitely getting to a point where you definitely will not enjoy writing this proof. Okay. Whereas going over the tactics was okay. If you had to write this proof, then that would not be so much fun. Okay. So although tactic is not required, you definitely don't want to write this proof. Tactics help you there. Okay, so that completes the functional programming part of the lecture. We will see more powerful functional programming later on. But is there any questions? We'll move on to the logic part of it.
Shall we take a 5 minutes break?
Yeah, sure. That's fine. I'll be here.
Yeah. So it's 3:30.
Just let me know when everyone is ready.
Yeah. So.
Okay, so in the rest of the talk, I am trying to, I go over the logic that is behind COC. Okay, so if you think of COC more as a logical system rather than as a programming language, how would you look at it? Am I audible, by the way?
Yes, you are.
Okay, so we already saw this. We had these two styles of doing things. One is definition. Foo is I'm defining foo to be a natural of type nat, and it's defined to be 2. And I have theorems of this kind, 2 is 2, which I prove through the tactic trivia. Okay, and this if I do a show proof, I will get what exactly is 2 equal to 2. Okay. The point here is I could have done it the other way. I could have kind of proved the 2 is 2 theorem by a definition, and I could have kind of defined foo through a tactic like this. Okay, so I could define 2 is 2 of type 2, numeral 2 equal to 2. So 2 is 2 is of type 2, and it is defined as this object EQRFL. So what this EQRFL is, we will see. Okay. Okay. So so this is another way to do the same thing. This part. Okay. Similarly, instead of using a definition, I could use a theorem and kind of use a tactic to kind of fill in the value for foo. So I'm saying foo is a nat, and I kind of prove it by giving a nat. And the exact tactic, what it does is it takes a term and just puts it there. Okay. So if you have a goal of some type T, and if you already have an object of that type, you can just say exact. Okay, so let's kind of go back to the propositions as types principle. Just like natural numbers, the term 2 equal to 2 is a type. Okay. And the EQRFL is a constant of this type 2 equal to 2. Okay, witnessing the statement that 2 equal to 2. Okay, so the 2 equal to 2 is a type. You should not think of it as a Boolean expression. It is not a Boolean expression. 2 equal to 2 is not true or false. It is a type. Okay, and you can kind of have an object of that type. If you take a statement like 2 equal to 3, for example, we know that it is false, right? 2 is not 3. So the way it works here is that you cannot produce an element of type 2 equal to 3, whereas you can produce an element of type 2. Okay. So the way you prove a mathematical statement is to produce an object of that type. Okay, mathematical statements are types, and you produce an object of that type.
Can you elaborate on this statement that 2 equal to 2 is a type?
See, the point here is, if you think about it, if you go by the proposition as types principle, any mathematical statement like 2 equal to 2 or 2 equal to 3 or 2 equal to 43 or 45 equal to 46, they are all mathematical statements. They might be true, they might be false in the true and false in the traditional sense. I'm not talking about true and false as in the Boolean sense. Okay, they might be true as a statement, they might be false as a statement. Okay. Now the question is, if I take a statement like 2 equal to 2, mathematical statement, how do I prove it? Okay. So in the propositionless types principle, you think of the statement 2 equal to 2 as a mathematical statement. It is a type. Okay, the connection is that. 2 equal to 3 is a different type. Just like nat is a type and string is a different type. 2 equal to 2 is a type, 2 equal to 3 is a different type. 2 equal to 2 has an inhabitant. You can produce a value of type 2 equal to 2. In this case, it is EQ-REFL. Okay. And because you could produce it, you can prove it. You can convince Coq that 2 is actually 2 by producing this object EQ-REFL, which it will see, it will look at EQ-REFL and realize that yes, this is okay.
Yeah, but let me ask you this question. So if you 2 has a type nat, and equality is a function which is nat arrow bool.
No, it is not.
No,
the equal to here is not a function nat arrow bool. It is actually what? It is nat arrow prop. It will take 2 nats and produce a prop.
Okay.
And that prop that you take for x equal to y, if you take that x equal to y in this sense, that will be a proposition or type which either is inhabited or it is not inhabited. If it is inhabited, you can produce such an object and prove that x equal to y.
So if you check equality dot in Coq, it will say what?
It will say for all a arrow prop. So it is generalized over all types.
And what is this prop? It is a basic type.
Okay, so prop is a kind of specialty of Coq. Okay, so you actually don't need prop if you just want to think about the proof system. Okay, but so what happens is that typically a proof assistant has a way to say things like, I mean, you would have to say things like for all type I want to do something. That kind of things you will have to say. Okay, so you will have a universe of types. Okay, there is no one universe of types, but that will lead to again logical inconsistency. But for time being, we can assume that there is a kind of a universe which consists of all types. Okay, that's not true. That's not true. It's a wrong statement. But just for kind of as a first approximation, you can think of it. Okay. Such universe types. One universe types is called props. Okay, and one universe types is called types. Okay, there are not, again, as I said, types is not a single universe. It is a hierarchy of universes. If you have a single universe, things will go horribly bad. Yeah. Okay. So the prop is that. Okay. And why does Coq distinguish between prop and type? It need not. Okay. If you take proposition as types principle literally, you should not distinguish between props and types. But there is some advantage of doing this when you look at extraction, because the point here is that see, there are mathematical statements that you want to prove. Okay. But you definitely don't want that proof to be carried along in your programs. You want to kind of erase them later on. Okay, when you produce the kind of actual program. Okay, so many of the terms in the code will be just there so that you can convince the proof assistant. They are not relevant for the actual computation. Okay, so in essence, what it means is that all the prop objects in your program will be erased off at the time of extraction. Okay, so that is for efficiency sake, right? See, for example, you do care about a natural number, whether it is 2 or 4 or 5 or 42 or whatever. Okay, but for a proof, most of the time you are not, you don't want to kind of distinguish between different proofs of, let's say, Fermat's last theorem. Okay, you want to say, okay, there is a proof, right? or some statement, you just want to say that you want to convince that that's correct. You don't really care. But if you don't erase them in your code, these will linger around and they will lead to inefficiency. And this is the kind of hack to kind of avoid it in some sense. Okay. So but for timing, you can think that there is only kind of one kind of types. Okay.
All right.
Okay. So that's a long answer. Okay. So the prop universe in Coq. So the universe of prop is the kind of universe of all propositions, and mathematical statements are objects of this quote unquote type. Okay. And any mathematical statement that you say like 2 = 2 or 2 = 3 or Fermat's last theorem or some such thing, they all live in prop. Okay. And producing an element of, producing a proof of A is just producing an element PF of the type A. Okay. So all you need to prove any theorem is to produce an appropriate, well-typed expression. That's all. Okay, so so on the logic side, you have like statements. Okay, now let's just go over this thing. On the Coq type theory side, you have the universe of props. You have mathematical statements like, for example, Fermat's last theorem. Okay, and they corresponds to objects FLT in prop. Okay, and how do you give a proof of FLT? You give an object of this type. Okay, suppose A and B are statement. You might want to say something like A implies B. Okay, now just think about it. How can I convince you that A implies B is indeed provable? I mean, how do I give a proof of A implies B? Okay, remember, A is a mathematical statement. So if I want to prove you A, then I should give you an element of type A. But I don't want to prove to you A. I want to prove to you A implies B, which means that I need to give you a way to transform proofs of A to proofs of B. Okay, so in the Coq world, this corresponds to the function type A arrow. Okay, because imagine that what does it do? It takes objects of type A and produces objects of type B. A function here produces a function of type A arrow B, takes objects of type A and produce objects of type B. If you think of objects of type A as proofs of A, you can think of the function as a mechanism to produce proofs of B from proofs of A, which you should think of. If I produce such a function, you should think of it as a proof of A implies B. Okay. Similarly, if I want to prove A and B, okay, so I want to convince you both A and B. How can I convince you that? I should give you a proof of A and also I should give you a proof of B, which means that I should give you a Cartesian product of the proofs of A and B. And similarly, if I want to convince you A or B, I need to produce some element in the disjoint sum of these types. Okay, so you can, if I go this way, I can get roughly the propositional logic. Pause here, and I will want to make this one important statement. When you think of it from the programming side, you might wonder what is the point of having a type with no inhabitants. Okay, but if you are in the logical world, okay, clearly those things make sense. These are statements which don't have proofs. Okay, a statement that does not have proof should be types which do not have inhabitants. So from the programming perspective, a type with no inhabitant is completely useless, right? Whereas in the logical world, this makes a lot of sense. Okay. Yeah. So that's about the connection between logic on one side and the type theory on this side. Any questions here?
Piyush, yeah, I had one question. So again, like trying to fit this whole idea into the context of programming. So you said that a particular statement is not, I mean, the proof is incorrect if we cannot produce an inhabitant of the
no. Just let's be precise here. Okay, I can prove a statement A by producing an element of type A. And getting Coq to accept it. Okay.
So what would be stopping Coq from producing element of type A if it's untrue, like unprovable or something? What were the cases?
No. So
That would
I'm
stop?
not claiming that I will be able to produce a counter example. I'm just saying that if the proof assistant will accept the proof, if it is so suppose you have a mathematical statement A, okay, and that is a type, okay. Now and you want to prove this claim. Let's say you want to prove Fermat's last theorem. I will show you a file where I have kind of written down the type associated with Fermat's last theorem. It is very easy. It's not a big thing. Okay. Now I have written a statement. It's a type. Okay. I am challenging you to write a term of that type. If you do that, you have proved Fermat's last theorem.
I see.
Okay. So the way you think about the programming in the context of proving is that think of the mathematical statement as a spec, okay, that your program has to satisfy. Okay, and producing a program that satisfies the spec is your proof. That is how you would think about it.
Got it.
Okay. Yeah. Any other question? Does this make sense?
Yes, it does. Thank you.
Let's move on. Any other questions? Okay. So now I want to talk about predicate calculus. Okay. I want to talk about predicates. Or maybe before that. Okay. Okay. So what are predicates? Now let's try to kind of see. Okay. Suppose we have a set A. Now I'm talking loosely now. Okay. I have a set A, let's say natural numbers, and I want to talk about a predicate on it. So what do I mean by that? For each A in A, I have a proposition P of A. Look, for example, P of n, if it is a proposition n equal to 42, then P of 0 is a proposition. What is that? 0 equal to 42. P of 1 is a different proposition. Okay, it is not P of 0, it is P of 1. And P of 1 is the proposition 1 equal to 42. P of 2 is a proposition 2 equal to 42, etc. P of 42 is the proposition 42 equal to 42. P of 43 is the proposition 43 equal to 42. Okay, these are different proposition, one for each value of it. Okay. Now, if I want to kind of convert this into the okay, now I start with a type A. Let's say natural numbers. Okay, how do I capture predicates of A? For each value of A, I should produce a type PA. Okay. Okay. So a type family is a function from A to the family of types, the universe of types. Okay. So again, if you are talking about mathematical statements, you will typically in Coq world write it as A to prop. And remember that prop and type is essentially the same, but for extraction. Okay. So, but let's be kind of you don't need to make that distinction right now. Okay. So a function from A to type is what a predicate on A is. Okay. So for example, if I look at that proposition that I had, okay, it is a function from that type, and that function is, it takes n and produces the type n equal to 40. Okay, so P0 is a type, P1 is another type, etc. Is this point clear?
Yes, that point is clear.
Yeah. So now, when you have such a type family, you can talk about what is a dependent function. Okay. So normally, what we have is you have a function, a domain and a range, right? So here, what happens is that you have a domain which is A, and the range. So if you give an input A, it will produce some element B, but this B's type will be dependent on A. It will not be, it will be potentially different for different A's. Okay. Now, this might look artificial, but you will see why this is very nice. Okay. So so I want to talk about things like a function whose value, whose output at A is of the type P of A. Okay, and that type is denoted by for all A in A PA. So this type, the for all A in A PA, is actually a type. Okay, it's the type of dependent functions. Does this make sense? And the for all is obvious. I mean, there is an obvious connection between this for all and the for all quantification. For all A in A PA is a type of dependent functions from A to PA. Okay, so the output type will vary according to the input. Does this make sense?
Yeah, so you have to be, I have few questions. So when you say output type may vary, you are treating P of 0 and P of 1 as different types, yeah?
They are different types because they are, if you think in terms of statements, they are different statements.
Yeah. But can it be like your function P on 0 is like bool and P of 1 is like int and so on? That's not what
you can do that also. That's also possible. How much of it is useful is a different matter, but you can define such things, and we will have one such silly example.
So your functions are not pure.
What do you mean by that?
Like in Haskell, that's not possible, yeah?
No, this has nothing to do with side effects or anything. It is just saying the input. You cannot say that f of A is of type P of A. Okay, f of A1 is of type P of A1. F of A2 is of type P of A2. Since A1 and if A1 and A2 are not the same, then potentially P of A1 and P of A2 can be different. Okay. In principle, if you take P to be the constant function, which takes X to B, then you get the ordinary functions, non-dependent functions. Okay. Just take P to be the constant type family, for example.
So no,
that is your function of ordinary.
Like you see, in a strict functional language, that will never happen. Yeah. Like you have the function are like very strict. Like there can't be like.
No. It is not. It has nothing to do with that. Let me give you an example. Okay. Yeah. Suppose I want to distinguish between lists of size n according to n. Okay. Okay, so I want to talk about lists of integers, but I want to or list of strings. Let's take a different type. Let's list of strings. But I want to think of lists of length 1 different from lists of length 2. Okay. There is a way to do that in a language where dependent types are supported. You can define a list type which is parameterized on the value type, the contents of the list, and also the length. So list of size 1 would be of different type than list of size 2. What this gives us is that we can write, for example, the head function as function which expects some list of length at least 1. You can say that.
Yeah.
So if you define it that way, then wherever you use head, the compiler will check that you have not taken head of a nil list, for example. Okay. So in that sense, you can do that kind of invariant encoding as well using dependent.
Okay. And why do you say that the type is for all A PA?
Yeah. So that will come next slide is about.
Okay. All right. That's right.
Okay. Okay, so now the point is that let's try to see what for all A in A, P of A as a mathematical statement is. I want to prove to you that no matter what A you give me, I will be able to show you P of A. Okay, what does that mean in the type theory world? This means that I should give you a function which takes A and produces an element of type P of A. Because how can I convince you P of A? By producing an element of type P of A. Okay, so dependent functions are essentially the proof of this for all A P of A. Does that make sense? Imagine like this. Suppose I want you to prove 2 equal to 2, right? What should I do? I should produce an element of type 2 equal to 2. What is it that I can do to convince you that for all a, P of A is true? I have to give you a function which, no matter what A you give to it, it will produce a B, which will be of type P of A.
Yeah.
Okay. Does that make sense?
Yeah.
So dependent functions are natural in that sense. Yes. Any questions here? This is not very difficult, but it is not something that people are kind of familiar with. So it might look a bit strange. But that is, if we kind of push the propositions as type principle, this is what it should be. The only way in which you can convince me that for all a, P of A is true is by giving a rule by which you can convert elements of A to values in P of A. So if I take an element X, I should produce an element of type P of X. Okay. And that is dependence function. Okay. So if you look at the left identity function, okay. So I can write it as a function like this. The left identity of n is the statement 0 plus n equal to n. I can think of it as follows. Left identity takes a natural number n and produces the type 0 plus n equal to n. So in that sense, left identity is a type family, and the proof of left identity for all n left identity of n is essentially this function which takes n and produces EQRF. Okay. So this EQRFL is a mysterious object. We'll see that, but essentially this is it. This is a dependent function. Okay, this EQRFL depends on n, so we will see that why all these things work out. But this is essentially left identity's proof written out as a dependently typed function. Okay, we will again interactively go over this. Okay, let me give you some nonsensical example of a type family, something that which Amal kind of alluded to. I can define a function t of n. It takes n and produces a type. And what does it do? If n is 0, it gives nat. If it is 1, it gives bool. If it is anything else, it gives nat star bool. Okay, I can write some nonsensical. It is completely nonsensical. It probably has no purpose, but just to illustrate that we can do this. Okay, I can do a check of t and see what the type of t is. I can compute t of 42. That will be a particular type, and I can also produce elements for these types. Okay, so we will see that in introduction. So let me summarize. Proposition as types, values as proofs. That is the main idea. Okay, and the predicates on A are captured by type families, because a predicate on A is what? For each value, it gives a mathematical statement. Okay, so if you push the proposition as types idea further, then predicates should take an A and produce a type which is dependent on A. The type is P of A is a type which is kind of, it's a function from A to types, and a dependent function foo which takes x in A and produces PA is proof of the claim for all x in A P of x. Okay, and tactics are just helpers to write the proof. That's it. And essentially what we want to do is write functions. So I have about 9 minutes, and I think I will now move on to the interactive session. In case you have a question or a comment, you can, I think, make it now, right now. I can't see the chat window, sorry, because when the screen is full, I can't see it. So if you have some questions, you should switch on your mic and ask, because otherwise I will not be responding. Okay, so then shall we move on to the interactive session?
Yeah.
Okay, so let me just now get the Emacs buffer. Is my Emacs buffer visible?
Yes.
Is it visible?
Yeah, yeah.
Okay. So let's go over this. Let me do this thing. Okay. So here is a definition foo is to. Okay. Yeah, I can do a check on foo. It will tell me that foo is match. I can do a compute on foo. Tell me foo is two. Okay. Okay. Now 2 is a proof of that kind. Trivial, and I can show the proof, and the proof is equivalent. So let's look at this curious character equivalent. Let's look at the type of this equivalent. So now you can see there are some question marks. So what are these question marks? So these question marks corresponds to what are known as implicit arguments. These are arguments that are there for EQRFL, but they are implicitly inserted by Coq. Coq will figure it out for you and insert that. Okay. I mean, that's what it is. So what it says is that there is an implicit argument A, there's an value X of type A, and EQRFL is of type X equal to X. Okay, and I can print by the way this equal to is just a syntactic sugar, okay, for EQXY. Okay, so notation X equal to Y is just EQXY. Okay, so I am EQXY is this inductive type. I could have defined this type if I didn't have it. EQA type, X in A to prop. And what does it have? It has only one constructor, which is EQRFL, which just says X equal to X. Okay. So this is how this type is defined. Yeah, so there is a question about indices and parameters. We will not go into the details of this, but the point here is that EQXY. So for example, if I take EQ2, EQ2 is a type family from NAT to prop. Okay, so let me just again switch off the company prop mode so that it will show it in text. Okay, so EQ2 is NAT to prop. I can also do check of Q. That is A to prop. Again, A is an implicit argument. Okay, so the above proof I can actually do by actually defining it as well. Define 2 is 2. It's just I can give the proof by actually doing an equal to and giving that term. Okay, and I can define foo by giving exact 2. Okay. So these are two ways of creating values of appropriate type. Any question here?
No.
Okay, so the left INT again, let's define it like this way and look at what left INT is. Left INT has type NAT to prop, so it's a predicate on NAT. Okay, and proof of left INT is for all n left INT of n. Okay, it's a dependent function which takes n and produces an element of type left INT of n. and left identity of n happens to be EQRFL with the appropriate n. Okay, so strictly speaking, just to make it more revealing, so if you put an at, for example, if you put an at, then what happens is that all the implicit arguments become explicit. Okay, so if I put here an explicit thing, let me make EQRFL explicit, then this will not work. I have to give all the arguments. Okay, so EQRFL has type for all A type x in A, x equal to A. It was expected to have left identity, so I have to give A to be nat and x to be n, and then it works. Okay. So this, if I give an at the rate in front of EQRFL, what happens is that it tells COP, don't put anything implicit, just make all arguments explicit. Okay, and when one does that, you can see that this is what the actual proof is. Okay, Coq is being helpful by trying to kind of fill in some of the details for it. Okay, if you check the proof of left identity, it will tell you that it is a function from n to left. It's a dependent function from nat to left identity. Okay, and this is a nonsensical theorem. I can just prove it. Computes it. Okay, so that's roughly it, and I think I'm almost out of my time. So I will just will give you an assignment for today, which is to prove. So you have to complete this program. I have written part of it, and I have left some small detail, which is the talk is too short for this, and I hope you will complete this by the next lecture. Okay, so let's kind of formulate the Fermat's laws. Yep. Yeah, so I define 0 or 1 as x being 1 or x being 0. I say that a solution x, y, z, a solution n for Fermat's last theorem is a set of numbers x, y, and z such that x power n plus y power n equal to z power n. I say that a triple of values x, y, z is a trivial if x is 0 or 1, y is 0, 1, and z is 0. Okay. And then I can now formulate let me write it this way. What is it? Is this? Let me make it slightly more interesting. Do that. I'll drop this proof. Okay, so we start the proof and then quote it because we don't have the time to prove it. Okay. Yeah. Yeah. So I conclude here. Let's stop sharing. There are questions. All the material that I have in this lecture, they are available on my GitLab profile.
Okay.
The link to that is available with the abstract that was sent around. So you can have a look at these things and you
All
can try
right.
it.
All right.
Yeah.
Okay,
So
then
any questions?
thank you. Yeah.
Hi, Dr. Kurur.
Yeah. Hi.
Yes, so I wanted to know that is there an introductory text that you would suggest that builds from lambda calculus and goes up to dependent type theory?
So what is your so see, there are multiple books are available and their focuses are slightly different. Okay, so the classical introduction to COC and proving programs correct is what is known as the software foundation series of books. Okay, you can see this Benjamin Pierce is the editor and many people have written parts of it. It's a group effort. Okay, so you can let's search on the net for software foundation. That has I think the first one is about programming and the second one is about programming language semantics or something. So you can have a look at it. It's a standard reference. Okay. I personally like the certified programming using dependent types. Adam Klippala's book, and again it's available online. You can have a look at it. The why I like it particularly well is because for certified programming there is a style of programming that it suggests. Okay, and I found it very powerful and very feasible to do non-trivial formalization for formalizing that. Okay, so the kind of style that it promotes is a style where all proofs are automated. Okay, by the way, I forgot to mention that one of the things that you can do with LTAC is that you can write your own tactics using LTAC. Okay, you can build on whatever tactics are available already and you can write your own tactics. And what essentially you do is you try to write tactics in such a way that you dispose of all proofs with just a mere crush. So the style of proof that Pala kind of promotes is a proof where you have a set of lemmas whose proofs are just crush. Okay, and crush is a LTAC tactic that you write. Okay, and there is a reason for that. The reason for that is when you try to prove correctness of programming examples, your programs undergo small modifications as the time goes. Okay, and if you don't automate your proofs, what will happen is that you will have to rewrite the proofs again and again if you just add one constructor, for example, in your network. So you should write robust automation scripts as well together with the programs. So it is like it's a process by which you design both the proofs and the tactics and the code together in one go. So that is the kind of thing that is I think a very good book if you want to get into certified programming kind of approaches. Then there are if you are more interested in the math side of things, where you are not that much keen on the programming aspect of it, but more trying to prove, let's say, some mathematical theorems like for example the odd order theorem. Every odd order simple group is every odd order simple group is solvable. It's a very famous group theory theorem, and this has been proved in COP, and they use a library called the MathComp library. Okay, so there is a book on MathComp. If you are more interested into the mathematical aspects of it, that is the book that you should read. Depending on what your focus is, you have multiple such options.
Okay, thanks.
Okay. So I think these software foundations, Benjamin Pierce software foundations, Klippala's certified programming using different types, and if you are more interested in the math part, MathComp. These three, I think, are probably the top references that I can think of.
Thanks.
Okay. And these are books on COP. There are other books available for Isabel and things like that, but I am not that familiar with those things. So, yeah, and their type theories are slightly different, and all those things are there.
Oh, I was thinking mainly a book that is not just focused on one system, but it's focused on type theory, calculus of inductive constructions in general.
most of these actual proof assistants have slightly different type theories. Okay. So there are some minor differences here and there. They are foundational in nature, and if you are more interested in trying to use them, these might not be that much of an interest to you. But if you want to know the type theory, then you will have to know these fine details, like whether the as I said, the type universe is not a single type universe. There is a gradation of type universe. There's a type 0, type 1, type 2, and type 1 is contained in type 2, type 2 is contained in type 3, etc. You have to have such a gradation, unless otherwise what will happen is that there is, just like the Russell's paradox, there is a paradox, I think it's called Girard's paradox, which will make the Girard's paradox, which makes the type system inconsistent. So what does inconsistent here means? It means that every type will become inhabited in your type system, and that is inconsistency, because then your false type will also get inhabited, and then that's not what you want. Yeah. So for example, in the universe, whether it is cumulative or whether it's a you support some other kind of universe, whether, so those things, the differences are there. Okay. And if you are more interested in trying to use it as a system, to kind of get familiar with the foundation so much and then work on it. Learning the underlying type theory is also interesting, but that's a very different kind of thing. What the books I suggested is more in terms of using the Coq proof system. When you use it, you will learn some of these issues, but you will not be kind of looking into the details of these. In the sense that they will mention that you have these type universes, where these universes create problem and those kind of things. But it will not talk about, I mean, how do you show that it's, how do you kind of prove the Girard paradox? I mean, that you have to have such a type. Those things it will not much about.
Okay.
Any other questions? Oh, okay, so tomorrow we will continue with this, and probably I'll do some more advanced programming kind of examples, and we will also probably look at one complete kind of toy compiler where we convert from expressions to kind of stack machine kind of compiler. So this we will do in the next 2 lectures. Okay.
All right. Thank you. See you. Let's see you tomorrow.
Same time, right? 2:30.
Yes, 2:30. Yeah. All right. Good night. Bye.
Okay. Bye.